Hey everybody, we are here with another live stream. We are doing office hours with Chegg. We're doing Organic Chemistry 1 office hours coming at you every Tuesday, 5 p.m. Pacific. And so, yeah, just as a reminder, if you want to check out the QR code on the top left, that will bring you to Chegg's site, and you can check out all of the office hours that they are offering. They're offering math office hours, all kinds of other stuff. So potentially you can get a lot of help for all of your courses this semester. Here we're going to be, once again, going over Organic Chemistry 1 concepts. Feel free to chime in the chat if you have some questions, if you have some things you want me to go over. As always, I have some problems ready to go that I want to talk about, that I'm aiming at sort of covering what most people will be covering in their curriculum right now. That's obviously every class is a little bit different in terms of the pacing, but I'm just kind of aiming at what I think, where I think you guys would be. And feel free to ask questions about what I'm going over. I can go back, explain something again, talk about a slightly different question, whatever it may be. So we are going to be doing Organic Chemistry 1 review for the next hour. And let's begin. So when we left off last time, we said that we were going to start digging into Grignard reactions. Grignard reactions are a very important reaction for building a larger carbon skeleton for a molecule because it is a great method of forming carbon-carbon bonds. Very old one. This was developed in 1912, I think was the reaction. So it's been around for a while, but it's still a classic. So starting out very simple. We did this one last time, just this first one, but let's go ahead and review. So we want to draw the product. Now, remember, with a Grignard reagent, the whole point of a Grignard reagent is that you're starting with an alkyl bromide or an alkyl chloride, and magnesium is inserting into that carbon-bromine bond in this case, and it is inverting the polarity of that bond. So whereas we are used to the carbon that is bound to bromine as being partial positive, right, electron deficient, because carbon is more electronegative than magnesium, in this case, it is actually partially negative. So Grignard reagents are a source of nucleophilic carbon. So that's going to be the nucleophile. Grignard reagents are nucleophiles, and then they tend to attack carbonyls. They have other substrates they can attack, but the classic is the carbonyl. So let's go ahead and draw the arrows. So we're going to draw the arrow from the carbon that is bound to magnesium. So from right there, that's where we're going to start, and we're going to go to the carbonyl carbon, and then we're going to kick that pi bond up there. So we get to be, because we kick that, we have a 1 2 3 carbon fragment. So MgBr plus floats off. Actually, technically, it would be it would be over here. So it will complex with the oxyanion. We don't even necessarily need to draw it. Just to be clear about what's going on, that MgBr plus will coordinate to that oxyanion until the aqueous workup. So that's what's next, the aqueous workup. So this is a second. This is when the reaction is done. When you throw the Grignard reagent in the lab, you get the oxyanion in solution, and then when you're confident that all of the reaction has gone to completion, you dump in some ammonium chloride or whatever it is, and that's going to go ahead and quench the reaction, we say, and that will transfer the proton to all of the oxyanions in solution, and you're going to get your alcohol product. So Grignards create alcohols. The product of a Grignard reaction is going to be an alcohol. And all we're doing is we're taking the alkyl fragment in the Grignard reagent and starting from the carbon that was bound to magnesium, that fragment will now be attached to the carbon that was the carbonyl carbon, right? This carbon right here used to be a carbonyl carbon, but that carbonyl has been reduced to the alcohol, and we have that 3 carbon fragment attached to that carbon. So that is what Grignard does. It's actually fairly straightforward, but then there can be different iterations. So let's look at a few different ones here. Okay, so this one here, we've got this benzyl Grignard reagent, right? When you have a phenyl ring plus a CH2, that's called a benzyl group. And so the benzyl is going to attack the aldehyde. Let's go over here, kick that up there. And so now we have 1, 2, 3, 4. We have the oxyanion, and we have the CH2 that attacked, and then the phenyl ring. So let's draw the phenyl ring out, right? You can write pH. You can draw the hexagon with the 3 pi bonds. You can draw the hexagon with the circle in it. I like to draw the one with the circle in it. It's easier, and it's actually kind of more accurate in a way because it displays the delocalized pi electron density. So that is the oxyanion, and then we're going to quench with a little aqueous acidic workup and get our secondary alcohol in this case. So there is our alcohol product there. So again, very similar. Okay, so now they're making you form the Grignard reagent. So first, we're going to get the Grignard reagent. And so magnesium simply inserts itself into that bond. Okay. So where you have Br, you now have MgBr. So mechanistically, it's kind of inorganic chemistry. We don't really need to talk about it. It's called oxidative addition. But that, yeah, we're just gonna understand that magnesium is inserting into the carbon-bromine bond. It is now in between carbon and bromine. And again, that inverts the polarity of the bond. Now we have this partial minus carbon where it was partial plus. And now, so what is it attacking? It's going to attack CH3COCH3. What is that? Well, that is acetone. So sometimes we're given something in condensed formula notation. We need to know what that is in line notation. CH3CO. When you just have CO like that, that means a carbonyl, right? When you have CO in between other alkyl, that means a carbonyl. And so this is going to attack right here, the carbonyl carbon. Kick that pi bond up here. And we will get, what is the best way to draw this? We can go phenyl, boom, boom, and let's do O minus, and then we have 2 methyls there, right? So what is the bond that formed? This is the bond that formed right here. Right, but we have to make sure that all that carbon content is still there, right? This was the carbonyl carbon on acetone. That carbonyl carbon had 2 methyl groups adjacent, so those better still be there. Always, always, always with Grignard reagents, if you get confused about the structure that you're drawing, just count the carbons, right? Make sure you didn't lose or gain any carbons, because all we're doing is we're forming a carbon-carbon bond. We're not going to get carbon atoms to magically appear or disappear. We're going to have conservation of matter here. So make sure you can number them if you need to. And so that's going to be handy. And then the workup, let's just do the workup step real quick. We're going to protonate that oxyanion. And there is our, let's put the hydroxyl on the dash, or on the dash, and a methyl on the wedge. So there is that. And then for the last one here, okay, so now let's see. This looks a little different. We've got these 2 bromocyclohexanes and 2 equivalents of magnesium. So it looks like we're going to get 2 Grignard reagents for every molecule of substrate here. And so first up, we're going to get our Grignard reagent. So we have MgBr. And what is this reacting with? Now we have an ester, right? We have CH3CO2. So CH3, here's the C, here's the O, here's the second O, and then a methyl. So this is an ester substrate. So one thing that we have to understand about Grignards is that they can attack aldehydes and ketones to give alcohols, but they can also attack esters. And when you have an ester substrate, it's actually an interesting case. And let's go ahead, let's just look at what's going to happen mechanistically so we can see why. So this is going to attack this carbonyl carbon, kick up the pi bond. Now, we don't have a lot of space here, so you could draw an intermediate where that has attached and you have the oxy anion. Let's just do this all at once, though. Say that comes back down and kicks off the alkoxy group. So let's kick off that alkoxy group. And what we end up with is the carbonyl has reformed, and now we have that there. Okay. And so what did we do here? We reformed the carbonyl. And so now if we have excess Grignard reagent in solution, remember it says that we have 2 equivalents of Grignard reagent for every equivalent of the ester substrate. That means that another Grignard reagent can attack, because Grignard reagents attack ketones, and we have a ketone. It's an intermediate, but it's there in solution. And so we don't have a lot of room here. Let's just do this. Let's put this guy here. Let's say we have MGBR. We'll just put it on that side. And let's have this guy attack right there. And apologies, I'm just going to have this go ahead and grab an H+, because, here, let's make the arrow go out here to an H+, just because we're running out of room. As you saw in these other ones, I did show the protonation step as a discrete step. Here, we're almost out of room. So let's just do this. And we are going to have the 2 cyclohexyl fragments connected to this carbon. What's going on? Stop. And then we have the new hydroxyl. We'll put it on the dash, and we will put the original methyl on the wedge. We're not creating a chiral center, so it is irrelevant which one we put on which. There will not be an enantiomer. So this methyl is here because there was a methyl to one side of the carbonyl, right? We started with this, there's this acetyl group here. And so in the end, that methyl is here. This methoxy group left, but that methyl that was adjacent to the carbonyl carbon is still there, and that is this methyl right here. But what we have done is we have taken an ester with 2 carbons on this side of the alkoxy, so those remain, but now we have attached 2 cyclohexyl fragments to it. These pink bonds, these are the 2 bonds that formed between the Grignard reagents and the substrate. And that happened because we had 2 Grignard reagents, 2 equivalents of Grignard reagent that were able to attack in succession, because the first time we attacked the ester, the carbonyl reforms to kick off the alkoxy. Since we have a ketone intermediate, another one attacks, and then that's how we get the tertiary alcohol product. Okay, so that's some Grignard. Let me see if I missed any questions here. Odin, I'm doing very good. Thank you for asking. Wandering Traveler, do some of the molecules not associated with the MGBR influence the reaction kinetics due to something like sterics? Sure. I mean, if you have a very bulky Grignard reagent, that reaction might be slower. That's a fair point. BTF Wayne asks, what would one use MGBR for? So MGBR is not a discrete compound. You have MGBR as part of the Grignard reagent. So like right here, we have a propyl Grignard reagent. That is that magnesium is bonded to that carbon. It's covalently bound. It's carbon sigma bond magnesium sigma bond bromine, right? That's a covalently bound moiety. Right. Cody says, just don't expose it to water. That's absolutely correct. And that is a very good point. Grignard reagents are carried out in strictly anhydrous conditions because a Grignard reagent will deprotonate water. So if you have this, if you have a Grignard reagent here, Actually, let's do the propyl just like we have here. And then we have water. We have a water molecule. This will go and take that proton, and we'll be left with simply propane. Uh, and so we will have destroyed our Grignard reagent. It will not be capable of doing any kind of reaction. Yep. Pi Trader asks, will you go into conjugated pi systems? I do have a question on this that I prepared that has one of those. So wait for that in a little bit. How are you able to do stereochemistry without a chiral center? No, so there would be stereochemistry to speak of if you were producing a chiral center. If the Grignard reagent is attacking a substrate such that the resulting alcohol is chiral, then you have to talk about a potential racemic mixture. So that's it. We're asked if why isn't there video translation to Arabic? This is a live stream. We're doing this live, and I do not speak Arabic. I apologize about that. Cody, no, yeah, there would not be any stereochemistry to speak of for any of these. None of these are chiral. So yeah, nothing to talk about here. Okay, I think that might be everything. Lucy, so we kind of we're kind of past SN1 and SN2, but just to tell you really quick, so the difference would be SN1. So if you have a very strong nucleophile, it can do SN2. If you have a very weak nucleophile, you're going to have to wait for the leaving group to leave first, generate a carbocation intermediate that is unstable enough such that even a weak nucleophile will react to it. So SN2 is one step, it's a concerted reaction. SN1 is two steps, proceeds via a carbocation intermediate. Please go ahead and go to my channel and go look at some previous live streams, because for a couple weeks in a row, we fixated pretty heavily on SN1, SN2, E1, E2, because those are the first mechanisms that you learn in OChem 1, typically. Okay, that's it. Okay, moving on. So Grignard is so important that we're going to check out some more, and we want to check out some different way. So sometimes you have reagents and you have to draw the product. Sometimes you have a product and you need to think about where that came from. So here, this says develop a plan to synthesize the following compound from an ester substrate. So spoiler, we're going to do Grignard, right? We just looked at Grignard. We're going to keep doing Grignard. So what was the thing that we need to understand about an ester substrate? When you have an ester substrate, you can do a Grignard, but you have two equivalents of the same Grignard reagent, right? It's not like you can throw two different Grignard reagents into the reaction mixture and dictate magically that you're going to get one of each or something like that. That's not the case. You have the substrate, you have the ester in solution, you have two equivalents of some Grignard reagent. It's going to attack twice, right? So if you're looking at a compound that is the product of Grignard being done on an ester, we have to identify two identical alkyl fragments, because those two identical alkyl fragments can have come from two identical Grignard reagents. So what are the two identical alkyl fragments? Well, that would be this ethyl group and this ethyl group, right? So we're saying that we can have two ethyl Grignard reagents. And then if that were the case, what would this other fragment be? Right? This has to have been the ester substrate. So and so this would be a 2-carbon ester. And we're not talking about the carbons on the alkoxy group. This doesn't matter, right? This can be methoxy, it can be ethoxy, it can be propoxy, it can be isopropoxy. Doesn't matter, because those carbons are leaving. The alkoxy group is getting kicked off when the first Grignard reagent attacks, when the first Grignard reagent coordinates. So all we care about is these two. We have 1, 2 carbons right here, right? These 2 carbons have to be on the ester right, the carbonyl carbon and the one next to it. So anytime you're doing retrosynthesis when you're looking at an alcohol product, the bonds that can be formed via Grignard are the bonds that connect to the carbon that bears the hydroxyl, right? So that's this one, and potentially this one, right? Depends what we're trying to do. But the carbon that bears the hydroxyl was the carbonyl carbon, and Grignard reagents attack carbonyl carbons. So only bonds that go to the carbon that bear the hydroxyl in the product can have been the bonds that formed via Grignard reagents. So this is what we have, right? We're gonna do MgBr, and we have our ester substrate, and we're gonna go boom right here, up there, come back down, kick off the methoxy, and we're gonna get our ketone, right? We've got our ketone intermediate. And now we can have another equivalent of Grignard reagent attack. That's going to go there. Boom. And we're going to get, let's draw it this way, like that. So this is just to be kind of geometrically accurate here, because that methyl, right, this methyl is this methyl right there. And then we have this 5 carbon chain there. And then let's just do our aqueous acidic workup. Let's quench this thing. And whoops, I don't like red for that. Let's do blue. And we have our alcohol. Yet again, we are not producing a chiral center. So this is the exclusive product. We do not have to talk about any enantiomers or anything like that. So we have to be able to do Grignard forwards, and we have to be able to do Grignards in reverse. Look at the product. Where did it come from? And just not to, this is a very important concept. So once again, you take the carbon that bears the hydroxyl. That carbon used to be the carbonyl carbon. Right. So only carbon-carbon bonds stemming from that carbon are the ones that can be retrosynthetically cleaved. In other words, the ones that can form in the forward direction. That's what we want to be. That's the most important thing here. Okay. See if I missed anything. Let's see. PyTrader PCC, I actually have at least one question on here that is talking about oxidizing and reducing agents, so we will talk about that. Isn't that lucky? P-Sway Beats, are we talking esters? So in the first question here, we talked about Grignard reagents coordinating to aldehyde and ketone substrates. That's kind of the classic thing. Although this fourth one had an ester substrate, and then this question also asked about something from an ester substrate. So an ester substrate allows you to coordinate 2 equivalents of the same Grignard reagent, whereas aldehyde and ketone substrates, only one, right? One attacks, you get the oxy anion, you quench it. Unless you quench and get the alcohol and oxidize, and then in a separate step react another Grignard reagent. But that's 2 different reactions. Cannot beat it, right? With the ester, that's all one pot. You throw the 2 equivalents of the Grignard reagent in there, they react in succession. It's all one thing. Peaceway says, please archive this. I want to go back and watch it over and over again. All of the live streams I am doing for Chegg are in the live tab on my channel. Just go click live and you will see this is the 7th one. So we've been doing this every Tuesday, and you will see all of the office hours that I've been doing for Organic Chemistry 1. You can go back and check out all the stuff that we've been talking about here. So hopefully that will be very useful to you guys. Wandering Traveler, how would you determine if a reaction like this actually occurs successfully? So, I mean, the short answer there would be NMR, right? In organic chemistry, after you do a reaction like this, you're going to quench, and then you're going to bring it into your separatory funnel, and you're going to do an extraction. You're going to do an extraction to get all the organic compounds out of there. Then you're going to throw it into a column. You're going to do your column chromatography so that you can isolate. I mean, you're right. There could be side products, right? So you're going to want to isolate your intended organic compound, and then you go and do an NMR, and you make sure that's what you got. So run the reaction, quench it, and extract. Do the column, do the NMR. That's kind of your like standard organic chemistry procedure. Anytime you do a reaction, different kinds of chemists have different techniques they use, but your boilerplate OChem lab approach is what I just said. Okay. Ronald, I I certainly can try to cater to any topics that you ask. I have a structured plan that I follow because otherwise it would be kind of complete chaos. I'm trying my best to follow an organic chemistry 1 curriculum that most people will be experiencing in if they're taking that this semester. Obviously, I'm just sort of going. I'm just going by what I think it would be. Every course people go at a slightly different pace. They might cover topics in a slightly different order. So I'm just kind of doing where I think you might be. But you may feel free to ask questions about what I cover. You can feel free to ask me to talk about something slightly different about what I cover. You can ask unrelated things. And if, as long as they're OChem 1 related, I may take a tangent and try to answer that. Okay, that's it. Okay, so let's do one more of these. So develop a plan to synthesize the following compound exclusively from propene. So, excuse me. So now we have a specific starting material that we have to abide by. So what is propene? This is propene, right? It's a 3-carbon alkene. And so if how many carbons are there in the product? 1, 2, 3, 4, 5, 6. Okay, so if there are 6 carbons in the product, it sounds like we need two equivalents of propene. And so if that is the case, what are the 2 fragments that we're probably joining together in the forward direction? So 1, 2, 3, that's probably going to be this and this, right? So if we pull those apart, what can those have come from? Well, let's see here. Well, this one bears the hydroxyl. So if we took that one back in time, that hydroxyl can have been a carbonyl. It can have been an aldehyde that a Grignard reagent attacked. And so let's make the other one the Grignard reagent. So let's do MgBr. Okay. Now, how are we going to do this from propene? So this guy, we want to take this back to the alcohol, and then from there all the way back to propene. This guy we can take back to the alkyl bromide, and from that I already have that drawn there. So let's just do that. So these are retrosynthetic arrows. We're saying back in time. If we've identified the 3 carbon fragments and we pull them apart, what reagents can they have come from? What reagents would go together to generate that product? Well, this aldehyde and this Grignard reagent would produce that product. So that's a valid retrosynthetic step. But now we need to go back even further because it said starting from propene. So can we go back to propene from each of these? Yes, we can. So let's start with this one. If we have propene, how do we get this secondary alkyl bromide? Well, that's easy, right? That's just HBr, right? We can just do a normal Markovnikov hydrohalogenation. We will get our secondary alkyl bromide. Let's do magnesium in diethyl ether and get our Grignard reagent. So we've gone from propene to our Grignard reagent, which is one of the two things that are going to react to give the product that we want. Okay, now we got to do the other one. So how do we go from that to the anti-Markovnikov hydration product? So that's going to be your hydroboration oxidation, right? This is peroxides and hydroxide. Right. So this is one of your flashcards that you memorize, right? We need to know the conditions for hydroboration oxidation. We didn't have to memorize anything to recognize that we can go from propene to the propanol. Let me actually erase this so it's not confusing. I'm going to move this over a little bit so that we can see it clearly. Right, we had to recognize that we could go from propene to the 1-propanol by doing an anti-Markovnikov hydration. Then all we had to do was remember what conditions we know of that promote anti-Markovnikov hydration. So we go to that, and then we can do, how are we going to go from the alcohol to the aldehyde? We got to oxidize, but we got to use a soft oxidizing agent because we don't want to go all the way to the carboxylic acid. We want to go to the aldehyde. So there is our aldehyde, and there is our Grignard reagent, and these two together go to our product. So this is a great one, right? It's making us think retrosynthetically, first of all, and then in the forward direction, it's testing our ability to recollect important addition reactions because we're going from propene. So if you have propene, what are you going to do? You got to do addition reactions. If you want to add functionality to an alkene, you're going to do addition reactions. So what do we know? We know hydrohalogenations, but are we going to do a Markovnikov or anti-Markovnikov? We know hydrations, but are we going to do a Markovnikov or anti-Markovnikov? As it turns out, we got to go Markovnikov hydrohalogenation because we want that secondary alkyl bromide because this is the carbon that is doing the attacking in the Grignard reaction. It's the central carbon of this fragment. So we want the Br there, not there. If it was the other way, right? If this was all a linear fragment instead of a branched fragment, if we had 1, 2, 3 carbons linear, like a straight chain propyl fragment, then we would want the anti-Markovnikov because then we could have a 3-carbon straight chain do the attacking. But we don't. We want the branched, so we wanted the secondary there. And then you just prepare the Grignard reagent. Over here, we knew that we wanted the anti-Markovnikov hydration product because of the structure of this fragment here. And so then we had to remember hydroboration oxidation. That's how we get the anti-Markovnikov hydration product. We get our primary alcohol. Then we needed an oxidizing agent, and we needed to remember that the soft one is PCC to go. I mean, there are others, but that's the classic. You only have to remember one to go from the primary alcohol to the aldehyde. Just memorize PCC. That one is going to get us the aldehyde we wanted in order to go in the forward direction. Now we have these two fragments, which again, remember our first retrosynthetic arrow gave us these two, which was valid because these two together make that. So as soon as we get there in the forward direction, we react them and you get the product you want. So that's a great one. These are very common types of questions when you're taking exams in organic chemistry because they test a bunch of stuff at once, right? It's all well and good to have a question that says, here's the Grignard reagent, here's an aldehyde, what do you get? You have to be able to answer that, obviously, right? But that's pretty easy. This takes a little bit more critical thinking, right? What is the bond we're going to retrosynthetically cleave? Well, it's the one connecting these two 3-carbon fragments. Then from there, how do we get all the way back to the allowed starting material? This is a very, very, very common type of question on an organic chemistry quiz. So this is good to be able to answer. All right, let's see if I missed anything. Okay. Wandering is asking about Diels-Alder. I have Diels-Alder in this set here, so hopefully we will get to that. Okay. Uh, Power then asks, what's left after the aldehyde is oxidized? I'm not sure what you mean. We're going from the primary alcohol to the aldehyde. That is the transformation. Pyridinium chlorochromate. That's the reagent that promotes that transformation. Okay, let's move on. So, number 4, identify the series of reaction conditions that will yield the following product. So, what do we have and what do we get? Well, let's see here. This is a 1, 2, 3, 4, 5, 6 carbon chain with a methyl group there. Excuse me. And then the product, we have a 1, 2, 3, 4, 5 carbon chain with the methyl and the bromo substituent right there. So the most important thing that we need to recognize when we're looking at this question, right? Sometimes students have a tendency to look at this and panic. I'm not sure what happened. I don't know what reagents to use because I'm not even sure what happened. Start out very simply, right? What do you have and what did you get? Count the carbons. We lost a carbon. Okay, that's very important because losing or gaining carbon requires a particular kind of reaction and not just transforming one functional group to another, right? It requires something where we're either building a larger carbon skeleton or fragmenting the carbon skeleton. So here, let's think really hard. What are we going to do that is going to lose a carbon? We want to lose this carbon right here. We want to get rid of it entirely. So what if we cleave this double bond somehow? What is a reaction we know that will cleave double bonds? Ozonolysis, right? Ozonolysis cleaves pi bonds, and the two carbons that were participating in the pi bond become carbonyl carbons. So this is going to yield this. And let's do a reductive workup so we can do dimethyl sulfide, right? Dimethyl, because we don't want to get the, well, I mean, actually, I'm sure there's a way to go that will, actually, it kind of doesn't matter, to be honest. I'm choosing the reductive. You can do the oxidative workup or the reductive workup. All that's going to change is the reagent we use next, but I'm going to choose reductive workup. That's what I like to do. So, oh, and let me not forget this methyl group there. So, we did the reductive workup, and now we have this aldehyde. So now we have the right number of carbons, 1, 2, 3, 4, 5, and the methyl, but we need to go from the aldehyde to this bromo group. Do we know of a way to go from aldehyde to bromo? We don't, right? But what's another transformation we can do? Why don't we reduce this? What if we use a reducing agent? Now you could use different kinds. I'm just going to go ahead and go the soft route. We're going to do sodium borohydride, and that is going to bring us to the primary alcohol. And so you could have done lithium aluminum hydride. That's just overkill. You will get that product, but we don't need it. So let's just do sodium borohydride. And the reason that we want to do that is we know of a reagent to go from alcohol to alkyl bromide, right? PBr3. So this is a great flashcard reaction. Potassium tribromide is going to transform a primary or secondary alcohol into the primary or secondary alkyl bromide. So PBr3 goes from OH to Br. That is one you definitely want to memorize. And it's also a very useful transformation because it has a lot of synthetic application. Like, for example, let's say you do a Grignard reaction and you make an alcohol and you want to take that alcohol product and turn it into a Grignard reagent to build an even larger carbon skeleton. Well, all you do is take the alcohol, use PBr3, turn it into the alkyl bromide, insert magnesium in there. Now you have an even bigger Grignard reagent that you can react with some other carbonyl containing compound and build another larger molecule. And then you could do it again if you wanted, right? So that's a very useful tool. Now, earlier I was saying we did the reductive workup. If you did the oxidative workup, you'd have a carboxylic acid here, but that's fine. But then you'd have to use lithium aluminum hydride. You would have to. Here, we could use either because either compound will reduce to the aldehyde to the alcohol. In real life, you would use sodium borohydride because there's no reason to use a stronger reagent than you need to. But if you had the carboxylic acid, you'd be forced to use something like lithium aluminum hydride because sodium borohydride will not reduce carboxylic acids. So that's just something to think about. Either pathway is totally fine. Whatever you ended up, if you were to settle on one over the other, that would obviously be completely acceptable, and you would get full credit either way you chose. But this is definitely the most straightforward way. Ozonolysis to cleave that terminal carbon. You get either the aldehyde or the carboxylic acid. You reduce to the primary alcohol. PBr3 gets you to the alkyl bromide. That's nice and clean 3-step. Very good synthesis there. Okay, let's see if I missed anything here. Okay. Enville asks, how does CH2 leave in the O3 step? So this is just like it's just like any other ozonolysis reaction, right? Usually we either have a longer linear molecule or a cyclic molecule with a carbon-carbon pi bond. The carbon-carbon pi bond cleaves, and the two carbons that were participating in the pi bond become carbonyls. So I mean, to be thorough, we are saying that we get formaldehyde byproduct, right? So that is there, right? It's not like the carbon doesn't disappear into thin air. You have a formaldehyde byproduct that we can separate, right? We would isolate and separate this out. Or, I mean, I guess you could continue one pot and then isolate the alcohol when you're done. But so, yeah, I mean, good question. It doesn't disappear into thin air. It's just not the fragment that we're concerned with. So we don't have to worry about it. We can just ignore it. Yeah. Okay, great. So let's do some really quick review, because some people last time were asking to backtrack a little bit. So just really fast, let's just do a couple Newman projections. This is stuff we covered in week 1, week 2, but just do one real quick just for those who missed it. So we want to do a Newman projection associated with the bonds indicated. So if we are looking at this carbon-carbon bond in this direction, on the front carbon, what do we see? We see that. So remember, you're positioning yourself in the plane of the screen, and you're looking in that direction towards the molecule. So directly above us, we see this bromine. The dash bond means that it's further away than the screen. So if you're in the screen, it's going down and to your left. So down and to our left is the hydroxyl, and then the implied hydrogen would be down and to our right. Sorry, what did I say? I meant the hydroxyl is down and to the right, and the proton is down and to the left, if that's not what I said. Then on the carbon that is obscured, this carbon is obscured behind this carbon, but we can see what it's attached to. So this methyl is directly down from that carbon. So these lines will go from the edge of the circle because they are connected to the carbon that is behind this front carbon. So CH3 is back there. Fluorine is on the wedge bond, so that is up and to our left. So fluorine will be there. And then the implied hydrogen on the dash is up and to the right. So there is the Newman projection for that one. Now let's go ahead and do this one. So we're looking at this carbon down this bond. What do we see? We are in the plane of the screen looking directly down. We have our methyl group up and to the right, right? That wedge bond is going up and to the right from our perspective in the screen. That's your fluorine. And then we have the methyl up and to the left. And then if we go to the back, we have this ethyl group projecting up. So you can either say CH2, CH3, or you can go boom, boom with line notation. That's also acceptable. Then down and to the right is our bromine. Down and to the left is our chlorine. So there you go. That is the Newman projections for those. Let's see what I missed. Lance, naming ionic compounds, that's really more of a Gen Chem topic. I do have at least a couple of tutorials on that in my OChem playlist, or sorry, Gen Chem playlist. Um, Oh, Hal asks, why is PBr3 better than doing substitution with a bromine salt? So PBr3 acts on hydroxyls. Hydroxyls are not good leaving groups, right? You're not going to do SN2 like this alcohol is not going to react with like NABR, right? A bromide is going to displace something that is a good leaving group, not a hydroxyl. So the reason PBr3 works is that oxygen coordinates to the phosphorus atom and kicks off one of the bromides. And now the oxygen is a good leaving group because it's positively charged. It's coordinated to the carbon and the proton and the phosphorus. So now bromide, the new free bromide can do SN2 and kick off. It's going to be HOPBR2 is going to be what's leaving. So it turns OH into a good leaving group. And it's actually a really clever reagent because oxygen attacks phosphorus, kicks off bromine, and then the part of the reagent that got kicked off acts as the nucleophile to kick off the original oxygen-containing group. So it's a very extremely useful reagent in organic chemistry. I hope that helps. Yep. Okay. So let's keep going now. Okay. So somebody asked about Diels-Alder. Let's do a couple of Diels-Alders here. Diels-Alder is very important. Eventually, you learn about electrocyclization reactions, and Diels-Alder is the classic. It is the classic, electron rearrangement reaction here. And so there are things that are easy about Diels-Alder, and there are things that are hard about Diels-Alder. The hard thing about Diels-Alder is that you have to always identify what the other stuff is doing, the parts of the molecules that are not reacting. Where do they go in terms of stereochemistry, all that kind of stuff? That can get a little tricky. The part that's easy is that the mechanism is the same every time. You have two pi bond, you have 3 pi bonds that are cyclizing to form 1 pi bond and 2 sigma bonds. So you are always forming a 6-membered ring. If you aren't forming a 6-membered ring with your Diels-Alder, you did it wrong. If you don't have a 6-membered ring in your Diels-Alder product, you did it wrong. It's got a 6-membered ring every time. And so let's just do the mechanism here. So we have so you always have a diene and a dienophile. So the diene is the one that has 2 pi bonds that are in a conjugated relationship. So we have a pi, it's pi sigma pi, right? They're not next to each other. They're alternating, double bond, single bond, double bond. So the diene has 2 pi bonds in that arrangement, and then the dienophile, the thing that loves the diene, has it can have more than 1 pi bond, but only 1 pi bond on it is going to react. So this will always be the mechanism for, and you know what? Let me go ahead and let's do this to make it perfectly clear. These dotted lines are where the new sigma bonds are going to be. So this pi bond goes to form another pi bond here. This pi bond goes to form this sigma bond, and this pi bond goes to form this sigma bond. So you are going from 3 pi to 1 pi and 2 sigma, right? 3 pi to 1 pi and 2 sigma. That is what is always going to be happening with a Diels-Alder reaction. So when you're drawing a Diels-Alder product, it can be a little bit daunting because these are the 6 carbons that are reacting, that are part of the one, 2, 3, 4 on the diene and 1, 2 on the dienophile. Those are the ones where chemistry is happening. So what's going on with all the other stuff? Well, always first draw the 6-membered ring that resulted. Now there's the diene is a 6-membered ring. So that 6-membered ring is still there, but let's not worry about that for now. Just draw the 6-membered ring that formed, right? So here is our new 6-membered ring, right? Now, so that's one, right? This carbon, this carbon, this carbon, this carbon, this carbon, and this carbon are now in a 6-membered ring together, and this is the new 6-membered ring. So what else is there? Well, first of all, right here, there's 1 pi bond that remains. So that we got to have that pi bond in there. There are two methyl groups over here, and they're still going to be there. And guess what? Stereochemistry doesn't matter because these are still sp2 trigonal planar carbons. So those are still flat. We don't have to worry about wedge and dash. Over here, we do have to worry about wedge and dash. Okay, well, actually, first of all, let's finish up here. There is another six-membered ring. So some of these carbons are participating in more than one ring because there was already a six-membered ring there. So these are your bridgehead carbons, right? We have let's thicken all of it there. So these four carbons are participating in this six-membered ring, the old one, and this six-membered ring, the new one. So that can be a little confusing, but that is how we have to draw that. Now, over here on the dienophile, or what used to be the dienophile, we have these two carboxyl groups. Now, with the dienophile, you have cis and trans potentiality, right? You have two carboxyl groups that were trans to one another on the dienophile. So they're going to be trans to one another on the product. So one of them is going to be on a wedge bond. So there's our carboxyl group there. And then the other one is got to be on the dash bond. Okay. So that's a lot, right? That's not the super duper simplest Diels-Alder that you can ever find, but this is ultimately what we want to be able to do. We want to be able to look at any diene and any dienophile, draw the product, and also go in the reverse direction, which is the next one. So once again, these ones with the pink dots, those are the six carbons that are participating in the Diels-Alder reaction. Therefore, those are the six carbons that are in the new six-membered ring. And it's the easiest way to do it is to draw that ring. You draw that ring that formed in the Diels-Alder reaction, then figure out what happened to everything else, right? Figure out where all the other substituents are now. But you always want to draw that six-membered ring first. Once again, if your product doesn't have a six-membered ring in it, something went wrong, because you're always going to have a six-membered ring in the Diels-Alder as a Diels-Alder product. And then the other thing here is this is typically driven just with heat, right? We don't need any other reagents. This is thermodynamically driven. It's just going to do this. Good question. Yes, this is going to have a stereoisomer where we have the dash up there and the wedge down there. Good question. So yeah, well, that would be actually the enantiomer. So that's not the diastereomer, but rather the enantiomer. It will be. It would not have a diastereomer, because for it to be a diastereomer, that would require for them both to be on the wedge or both on the dash, and so that would mean they have to be cis. But that would violate the stereochemistry rules of the Diels-Alder. If the two carboxyl groups were trans on the dienophile, they're going to be trans on the product. So we cannot get a cis stereoisomer. We cannot get a diastereomer, but we will have the enantiomer, which will be the dash up here and the wedge down there. So good question there. Let me see if I missed anything. How do I write so accurately with the pointer? Thank you for saying so, because I think I'm not that good at it, but I've been practicing for a while. So yeah, I have this stylus pen and a tablet, and I do my best. I don't have very good handwriting, but I get by. Michael, how does one understand the product of a Diels-Alder reaction? That was kind of my best shot at explaining it. So if you have, and also Yeshi, if you're confused, if you guys can try to, formulate a little bit more of a specific question. If there is a specific part about what I was talking about that was confusing. Michael asks, so how you organize the lobes of dienophile is how you get so many possible products. So I don't know what you mean by lobes. I think maybe you mean by these substituents. So in this case, the substituents on the dienophile were trans, so they're trans on the product. If they were cis, right? If this carboxyl was pointing this way instead, that would be a cis dienophile. It would be cis on the product. And we would get the two wedge or two dash. That's actually called the endo or exo product. We can try and talk about that next week. Yeah, so that's it. So now let's check now let's go the other way. So we have our Diels-Alder product, and So admittedly, sometimes if you see this on a quiz, well, what the heck? I don't have any information. What kind of reaction happened to yield this? Maybe sometimes they'll give you a hint, right? They'll say Diels-Alder because admittedly it is pretty ambiguous. But a tip-off is you do have a six-membered ring, and that six-membered ring has a pi bond in it, which can have been a pi bond that remained after Diels-Alder. So that's what it is. So here, if we're going backwards, what are the bonds that we can retrosynthetically cleave? We know that in the forward direction, Diels-Alder makes six-membered rings, and it's going to make a six-membered ring that has one pi bond in it, right? Because you go from 3 pi bonds to 1 pi bond and 2 sigma bonds. So if this is the pi bond, the pi bond is here, so this must be the six-membered ring that formed in Diels-Alder, not this one, right? This is not the one because where is the pi bond? The remaining pi bond. It doesn't make sense. This is the one that formed via Diels-Alder. So if this is the pi bond that formed, then these are the sigma bonds that formed. So these are the ones that we can retrosynthetically cleave. So we're going to break those sigma bonds and pull it apart. And if we do that, we are going to get this and this. So we had a six-membered ring diene with that one pi bond, and then we had our very simple classic Diels-Alder diene as well. So, and we can go ahead and just prove to ourselves that this works, right? We can do the arrow there. It's kind of hard to, let me just move that pi bond a little bit. So in the forward direction, if we do push that one there, and let's actually, this can be useful, right? Oops, no, that's not what I want. Right there, we can do that. And then, so this pi bond goes here to form this sigma bond. This pi bond goes here to form this sigma bond. In the forward direction, we do end up getting this product. So that works. So when you first learn Diels-Alder, it's a little bit confusing, but once you really get the pattern down, it's actually pretty easy. You're just forming a six-membered ring or undoing a six-membered ring. That's all there is to it. And then we just see where that pi bond is to know what's going on. So it gets a little trickier. Also, maybe next week, I'll try to include one or two where we're doing Diels-Alder with an alkyne dienophile, because you can have that, right? You can have an alkene dienophile, and what ends up happening is only one of the pi bonds reacts, and you have a pi bond remaining. So that actually, that makes things a little bit trickier. So we'll check that out next time. Let's see if I missed anything. Cool. Okay. So let's just hit one more really quick here. We only have 2 minutes, but this is a really fast one. Specify the oxidizing and reducing agents that would carry out the following reactions. So first of all, we have to recognize if it's an oxidation or reduction. Here we're going from a secondary alcohol to a ketone. That is an oxidation. So which oxidizing agent would we use? We could use a multitude. We could use most of the possible oxidizing agents. Let's just go ahead and put PCC. That's going to be fine. You can also use a stronger one because we're not going to be able to get a carboxylic acid. It's going to be a ketone no matter what. Okay, here we're going from, what did we have? We have a ketone and a carboxylic acid. We're going to an alcohol, and the carboxylic acid remains. So that means we use the soft, first of all, it's a reduction, right? Ketone to alcohol is a reduction. And we used a soft reducing agent because we were not able to reduce the carboxylic acid. So that one's going to be sodium borohydride, because if we used a stronger one, we would have reduced both moieties. Now, how about this one? We have a ketone going to the secondary alcohol, and we have a carboxylic acid going to the primary alcohol. So we did a reduction, and we reduced both functional groups. So now we need a strong one. We need lithium aluminum hydride. We need a strong one because a soft one is not going to be able to reduce the carboxylic acid. Sometimes you want that. Sometimes you want to selectively reduce. Sometimes you want to reduce it all. Depends what you're trying to do synthetically. So that would be that one. And then over here, we're going from the primary alcohol to the carboxylic acid. That's obviously an oxidation. And we need a strong oxidizing agent. Let's say something like potassium permanganate. That will do it because a softer one, where if we went to the aldehyde, that would be PCC. That's a soft oxidizing agent. We need a harder one because we're going all the way to the carboxylic acid. So that would be potassium permanganate. Okay, so that is our time. Once again, we are doing Organic Chemistry 1 office hours with Chegg every Tuesday at 5 p.m. Pacific time. Go ahead and check out the QR code there if you want to see what other office hours Chegg is offering. They're doing math. They're doing all kinds of other topics, so you can get help for all of the courses that you are taking this semester. Otherwise, I will see you next week. We're going to pick it back up here. We're going to do probably more Diels-Alder. I'm thinking we're going to dive into some enolate chemistry. That's probably the next topic. That's a bulky topic, and we're going to check out